device, but if you notice in the question, they've already done that for us. So all we have to do is size our wire. We're going to head to our primary ampacity table and find a wire that is good for 118 amps. We go down, we slide down the 75-degree C column on the copper side, and we're going to find that we select a number 1. And in the testing center on the electrical exam coach website, you'll have more variants of this and practice of this, but that's how easy it is with commercial. First size the breaker based off the known load, and then you're going to size the wire. It really is that simple. Now let's dive into residential and learn a few more codes. Now let's learn how to size dwelling unit services and feeders in between 1 and 400 amps. This applies to single-family dwelling units and the individual units of two-family and multifamily dwelling units, and it's affectionately called the 83% rule. The next few slides are very dense, so I want you to slow down, take your time, watch it as many times as you need, but I know that you can do it. Keep up the great work. Let's imagine that we have a dwelling, and the first thing we're going to do is find our total connected load. Let's imagine that it's 47,000 VAs on a 240 volt system. That gives us 195.83. We would round up to 196 and go size our main breaker. And the main breaker would be a 200. That's the next standard size. We now have a 200 amp service. Now the next step normally would be to size the wire at 196 amps, right? That's our known load. We can just follow our normal ampacity rules. Well, not with services that are in between 1 and 400 amps. And let me show you what I mean. Let's all head to page 800 if you're in the 17, this table if you're in the 20, and this table if you're in the 2023. This is technically called the 83% rule, but I'm not going to force you to do the longhand math. I'm going to take you to these tables that are in the NEC that are almost like a cheat sheet that makes this super easy to apply and understand. Let's get to it. Once we get to our table, we work all of our tables from top to bottom, left to right, using those headings to navigate the table. On the left-hand side, we're going to find the size of the service and feeder, and this is listed in amps. And you'll notice that it only goes to 400 because the rules that we're learning right now only apply to services and feeders that feed the entire dwelling in between 1 and 400 amps. And I've got a great graphic illustration in the next slide to show you when it does and does not apply. On the next column over, we're going to see the copper side if we decide to use copper, and then aluminum if you decide to use an aluminum. So what you do is size your service. You come down here. Let's imagine it's a 100 amp service and you want to use copper. You slide over and it tells you what size wire to use. It makes it super simple. Now let's put it to practice. Now let's find out when this rule does and does not apply. Let's imagine that we have a single family dwelling. We have the meter socket outside, we have the riser, and we have a back-to-back panel, kind of an old school setup. We have the wire going up the riser and the wire going inside. Technically, this is all service wire all the way to that main breaker, and the 83% rule does apply here, as long as it's in between 1 and 400 amps. Now let's imagine that we have a main breaker outside, we have the service riser, and we have a main sub panel inside. We have the riser wire and the wire going inside. The 83% rule applies to all this wire. You can apply it to the wire going up the riser, and you can apply it from the meter disconnect combo to the first main sub panel. Now the rules with this is that it has to be the panel that feeds the entire structure. You're not allowed to use it on other sub panels or on any sub panel that does not feed the entire structure. You have to be very careful with that one. So we're allowed to apply it on this one on the left for the whole wire. We go use that table and size our wire based off the table. And the scenario on the right for all of that wire there for the service itself, and then also for the main feeder, as long as that panel that it's feeding is feeding the entire structure. You would go to that table, do your cheat sheet, find your size breaker, slide over, and you'd be able to use that size wire. Let's dive into two-family and multifamily. This is 1 through 400 amps, and this applies to the feeders only. The feeder must feed the entire dwelling. Let's imagine that you have an apartment here on the right-hand side, and it's attached to the larger apartment structure. That's where the main service is. Let's imagine that you have your meter center out here. you have your service riser, and then you have your wire going up. That wire there, the 83% rule does not apply. You're going to use all of the previous rules that we learned before and apply those. But the individual feeder going into that unit the 83% rule does apply. And the beauty of this is it allows you to save money in the long run. Whether you're doing single family dwellings only or you're doing the individual units of the apartments, you're going to be able to use a smaller wire based off that table than you would if you went and sized it like normal. And over a year's time, that could save you a lot of money. So that is when the 83% rule does and does not apply. What size copper wire and main breaker would you select for a service with a total calculated load of 47,000 VAs for a single family dwelling on a 120 240 volt system with 75 C terminals? Step 1, we're going to find our total connected load. In this case, they've given it to us, but we have to divide to get our amperage. When we do, now we can check for demand factors. And in this case, we do have a demand factor. Is this in between 1 and 400 amps? Yes. Is this on a single family dwelling? Yes. So the 83% rule does apply. So we get to use the table. Step 1, we're going to size our overcurrent protective device. And we're going to head to table 240.6a. We have a 196 amp known load. We're going to choose the next size up and put it on a 200. Now we can use our cheat sheet table. When we head there, we're going to size the wire. Step 1, we're going to be on the left-hand side and find our size breaker. Then we're going to come over to the copper column because that's what it requested. And we're going to find that we need to put it on a 2-aught. And in this case, we would have 2-aught copper on a 200 amp service. Great job. What size aluminum wire and main breaker would you select for a service with a total calculated load of 47,000 VAs for a single family dwelling on a 120 240 volt system with 75 C terminals? Step 1, we're going to find our total connected load. In this case, they've given it to us, and we're just going to divide, just like we did before. Now, we check for demand factors. Is this in between 1 and 400 amps? Yes. Is this on a single family dwelling or the individual unit of like an apartment? Yes. So, the 83% rule does apply. And we're going to go size our overcurrent protective device. We end up putting it on a 200 amp breaker, just like we did before. But now we have to be careful because the question is asking for aluminum. We head to our cheat sheet table. We start on the left-hand side, and we're going to find our size breaker. Then we have to slide all the way over to the aluminum column, and we're going to find out that it's a 4-aught aluminum. Great job. That's the end of lesson 9.4. When it comes to these type questions, the only way to beat it is through repetition. And the best way to do that is at electricalexamcoach.com. We teach you so much more inside of the quizzes that we don't get the chance to cover inside the videos. There are so many different nuances, different levels, and just topics that we haven't covered on video that we cover inside of those quizzes that are in the testing center at electricalexamcoach.com. I am the Electrical Code Coach, and my bargain is that these videos will add value to you, and you will in turn add value to others. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com. And this is lesson 9.5 in our video series. And in this lesson, we're going to be learning about bundling adjustments and ambient temperature corrections. These are a subset of ampacity. And remember, ampacity is just how many amps the wire can handle safely under its conditions of use without exceeding its temperature rating. Bundling adjustments work like this. When wires are bundled, like in a pipe for example, they have less ability to dissipate the heat, and it reduces how many amps the wire can handle safely. Ambient temperature corrections are like this. If wires are run in an extremely hot ambient temperature, it reduces how many amps the wire can handle safely. We're going to learn about these one at a time. Let's get to it. Let's dive into bundling adjustments. Let's take a look at our primary ampacity table. I want you to turn there now. And these values down below this table are true if, well, the question is if what? If you look at the paragraph above the table, the one that I said we would come back and look at later, it's got some parameters there. It says, hey, These are the ampacities of these conductors if, and the first if that we're going to look at is if there are not more than 3 current carrying conductors inside of a cable, pipe, or even buried in the earth together. Let's take a look at it. Let's imagine that we have a piece of conduit here and we pulled in a black, red, blue, and an equipment grounding conductors. What this table is saying is that those ampacity values listed down below in this table are true as long as you have not more than 3 current carrying conductors in a cable, pipe, or raceway. If you do have more than that, then we have to do what's called a bundling adjustment. Let's learn about our bundling adjustment table. Head to this respective table depending on your code cycle. When we get there, we're going to find that it's very easy to read. Reading all of our tables from top to bottom, left to right, we're going to start here on the left-hand side, and this is our number of current carrying conductors. Let's imagine we have this conduit, and we end up with 6 current carrying conductors. So we're going to slide down until we find our range, and we fall in the 4 to 6 range. Then we need to slide over and find our adjustment factor, which is just another demand factor, which is something you're very familiar with at this point in the program. Let's imagine we have a wire that's 50 amps. We take that 50 amp wire and we multiply it by 0.80, which was our demand factor. And we end up with a wire that is now only good for 40 amps. What they're saying is because the amount of wires inside of this pipe or cable that the wire cannot dissipate the heat safely. So you have to reduce how many amps the wire can handle. So the new allowable ampacity of this wire is only 40 amps. Up until this point, we've had all hot conductors inside of our conduit. But what happens if we add in a neutral? Is it considered a current carrying conductor? What about grounding conductors? Are they considered current carrying conductors? Well, let's learn how to count conductors now. Now let's learn about current carrying conductor counting, because we're only going to be counting the current carrying conductors. You may get a question on your exam that gives you the number of conductors. That's easy. You're going to go to the tables and do the math. But you may get a question on your exam that asks you in a scenario of wires, how many of them are current carrying conductors? The first one's easy. All ungrounded conductors. All of the hots are going to be considered current carrying conductors under normal circumstances. The second one is the neutral of a line to neutral load, meaning if we have a light bulb and it draws 1 amp on a 120 volt circuit, there's going to be 1 amp going in on the hot and there's going to be 1 amp flowing back on the neutral. So it is as well a current carrying conductor. Same thing with a 3-phase 4-wire neutral. We're not going to be dinking around trying to calculate the unbalanced load. We're just going to count it as a current carrying conductor. Then the 3-phase nonlinear neutral load. Nonlinear loads come from large fluorescent lighting or from large computer data centers. You're going to count its neutral as well. Grounding conductors, no, they do not count. And that's one of the easiest ones. You don't have to count those as a current carrying conductor. If we have no adjustment will be made if we have nipples that are 24 inches or less. Let's imagine we have a panel over here on the right-hand side. We put a panel on the left side. We want to run a short nipple that's 24 inches or less. This does not count in our bundling adjustment. Now let's talk about choosing from the right column. And this is the last step before we're actually able to start doing questions. Up until this point, we've always chosen, most of the time, from the 75-degree C column. Now, there'll be times that we choose from the 60, and this is where we start choosing from the 90. 99% of the time, you're going to choose from the 90 anytime that you're doing bundling adjustments or temperature corrections. We're going to choose from that 90-degree C column. We're getting ready to do practice questions, and you'll understand that more fully as we proceed. What is the allowable ampacity of a number 4 copper conductor with 9 current carrying conductors in a piece of 1-inch EMT? Step 1, we're going to verify that our conductors are listed in the 90-degree C column. We head to our primary ampacity table on the copper side, and we make sure that THHN is listed. If it's not listed there, for the purpose of exam prep, I just want you to go to whatever column that it is listed in and do the math. Now, we're going to find our starting ampacity in the 90-degree C column. We head to our primary ampacity table. It's wanting a number 4 conductor, so we start on the left-hand side. We're going to come over and we're going to tee off with a 90-degree C column, and we're going to find out that it is 95 amps. That's our starting ampacity. Now, we must check for demand factors. Are there more than 3 current carrying conductors? There are, so we must apply the demand factor. We're going to head to either table depending on what code cycle you're in. It is our bundling adjustment factor table. And when we get there, we're going to start on the left-hand side. We come down and find our number of current carrying conductors. Then we cross over and find our demand factor. Now we can get to work. We take our starting ampacity, we multiply it by the demand factor, and that gives us a new allowable ampacity of 66.5 amps. A wire that was once good for 95 amps, because of it being bundled in this pipe, is now only good for 66.5, and we select A. Great job! What is the allowable ampacity of a 1-aught XHHW copper conductor with 13 current carrying conductors in a piece of 2-inch RMC? Step 1, we're going to verify that our conductors are listed in the 90-degree C column. When we head there, we find that XHHW is listed, so we're going to find our starting ampacity. We head to our primary ampacity table. We're on the copper side. We start until we find 1-aught on the left, then we cross all the way over to the 90, and we find that it's 170 amps. Now, we check for demand factors. Are there more than 3 current carrying conductors? There are, so we must apply the adjustment factors that are listed in these tables. We go to our adjustment factor table. We're going to start on the left-hand side and find our number of current carrying conductors. Then we cross over and find that it's 50%. We take that and do our math. We take our starting ampacity multiplied by the bundling adjustment factor. Then we're going to have a new reduced ampacity of 85 amps. Great job! What is the allowable ampacity of a number 6 THHN aluminum conductor with 6 current carrying conductors in a piece of 3/4 inch EMT? Step 1, we're going to verify that our conductors are listed in the 90-degree C column. We head there now, but we're on the aluminum side because the question requested aluminum conductors, and we find that THHN is there. Now we find our starting ampacity in the 90-degree C column. We head to our primary ampacity table on the aluminum side, and we slide down until we find a number 6. Then we're going to come over and we're going to cross over and find that our starting ampacity is 55 amps. But we must check for demand factors. Are there more than 3 current carrying conductors? There sure are. So we're going to head to our bundling adjustment factor table. When we get there, we're going to find our range of conductors. Then we're going to cross over to the demand factor. Now, let's just do the math. We take our starting ampacity multiplied by 0.80, and that gives us a new reduced allowable ampacity of 44 amps. Let's get to it. That's the end of lesson 9.5. I want to let you know that you're doing a great job. Keep up the good work. Keep grinding. If you need anything from me, whether it's mentoring, coaching, or any way that I can help you in life or business, you can always just email me at electricalcodecoach@gmail.com or shoot me a call or a text at 423-895-3247. If you don't get me, leave a voicemail and shoot a text. I am the Electrical Code Coach, and my bargain is that these videos will add value to you, and you will in turn add value to others. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com, and this is lesson 9.6 in our video series. In our previous lesson, we learned all about bundling adjustments and how to derate them when wires are bundled inside of a pipe, cable, or raceway. In this lesson, we're going to be learning about ambient temperature corrections. It's very similar. We just pull from a different table, but it's the same style demand factor process that we've been doing this entire program. Ambient temperature corrections are like this. If wires are run in an extremely hot ambient temperature, it reduces how many amps the wire can handle safely. And let's not forget the basic definition of ampacity. It's how many amps the wire can handle safely under its conditions of use. Let's get to it. Let's take another look at our primary ampacity table. In the last lesson, we learned about the first part of the note that's at the top of the table. and it says that these values are true as long as you don't have more than 3 current carrying conductors. But there's a second piece to this. Now, if you're in the 2017, it's at the top of the table. If you're in the 2020 and the 2023, it's at the bottom of the table. And what it's stating is that these values are true in this table as long as you're in an ambient temperature of 86 degrees Fahrenheit. Anytime you get outside of that ambient temperature, you're going to have to do an ambient temperature correction. Let's imagine that we have this circuit here, black, red, blue, and an equipment grounding conductor. Well, we know from the previous lesson that we will not have to do a bundling adjustment on this one because there's not more than 3 current carrying conductors. But what if we were in a factory who was making a plastic process and they had to have that room at exactly 115 degrees all the time for all of the machines to function properly? That's what we're going to learn about in this lesson when you run into those scenarios and you're pulling circuit conductors. Now let's learn about our temperature corrections table. Go ahead and head to your code cycles table number now. Pause the video if you need to. When we get to the table, we want to verify we're in the right table. And how we do that is make sure that we're in the table that says 86 degrees Fahrenheit. We do not want to be in the table that says 104 degrees Fahrenheit. The table looks identical, but it'll have all the wrong numbers that you need. So you want to make sure that you're in the table that says 86 degrees Fahrenheit. Then if you're able to in your state, I want you to highlight that table. Just highlight the title of it. So when you're flipping through and doing these questions, you're going to know that you're in the right table and you don't have to second guess yourself. Once we know that we're in the right table, let's break down the table. On the left-hand side, we're going to find our column in Celsius. And that's if your actual ambient temperature is in degrees Celsius. You would start on the left-hand side, find the degrees in Celsius, and then finish the process that we're getting ready to learn. Across the top, you'll see a 60, 75, and 90 degree C column. And those correspond with the 60, 75, and 90 degree C columns of our starting ampacity table. Then on the right-hand side, you'll notice degrees Fahrenheit. And that's if your ambient temperature is listed in degrees Fahrenheit. Let me give you an example. Let's imagine that we have this circuit here with our black, red, blue in it. And we have our equipment grounding conductor. Then let's imagine we're in an ambient temperature of 115 degrees Fahrenheit. We would start on the right-hand side and we would find 115 degrees. Then we would come over to the 90 degree C column and we would find our correction factor. And all it is another demand factor. And let's imagine that we had a wire that was 50 amps before we started. We found out that it was installed in an ambient temperature of 115 degrees. And we found out that our correction factor was 0.82. All we would have to do is take our starting ampacity, multiply it by 0.82, and we would end up with a new allowable ampacity of 41 amps. Great job. Let's talk about choosing from the right column. Just like with bundling adjustments, 99.9% of the time, we're going to be choosing from the 90 degree C column for our starting ampacity. And then we have to make sure that we choose from the 90 degree C column in our temperature corrections factor table. In the event of it not being listed there, we're likely going to choose from the 75 if it's listed there, but we have to make sure that we choose from the 75 over here as well. But that would be under very rare circumstances when you are in the testing center. But I just want you to know about it just in case. And one thing that I do want to mention at this point in the program is NM cable. NM cable is Romex, and it is actually allowed to be chosen from the 90 degree C column. Romex is just a trade name. They also have Southwire and other trade names. But in the code book, it's called NM cable. And for the purpose of bundling adjustments and temperature corrections, you're allowed to choose from the 90 degree C column when doing those calculations. What is the allowable ampacity of a THHW number 6 copper conductor with an ambient temperature of 142 degrees terminating to 75 degree C terminals? Step 1, we're going to verify that our conductors are listed in the 90 degree C column. We head there and look for THHW, and sure enough, it's right there. Now we're going to find our starting ampacity in the 90° C column. We head back to that table. We're going to start over here and find our number 6. Then we're going to cross over and find its ampacity in the 90° C. And in this case, it's 75. We're going to take our number 6 at 75. Now we're going to check for demand factors. Is the ambient temperature greater than 86 degrees Fahrenheit? It is, so there will be a demand factor. We're going to head to our respective table depending on our code cycle. And we're going to go find our correction factor. When we